Imagine particles with energies greater than anything produced by human laboratories. Such particles travel across light years through the vastness of space, occasionally colliding at the top of our atmosphere. This collision creates a shower of very energetic particles that pass through our bodies every single second. Our universe is full of strange phenomena. This is among the strangest. I'm talking about the discovery of cosmic rays, which were discovered over 100 years ago. Welcome to my science communication videos. The theme of the first few videos will be astroparticle physics, basically the theme that tries to understand particles from outer space. In this video, I'm interviewing an expert in the field of cosmic rays. Dr. Katherine Rawlins is a professor of physics at the University of Alaska Anchorage. We will discuss the challenges of detecting cosmic ray showers and the immense engineering efforts required to build a massive detector in the South Pole for identifying the tiniest particles. Additionally, we will explore the potential dangers of cosmic rays and the remarkable steps taken to understand their interactions. A good starting point is to understand what the IceCube detector is and how it functions.
Well, IceCube is a multi-purpose observatory, a particle detector located at the South Pole in Antarctica. And it's a bunch of light sensors deployed both deep in the glacial ice of Antarctica, but also in some tanks on the surface.
On top of that, IceCube is the largest neutrino detector in the world. How large? Imagine a cube which is 1 kilometer on each side, so a massive 1 cubic kilometer. This colossal detector is also buried deep underneath the Antarctic ice. Its construction was a fascinating feat of engineering.
At the South Pole Station, we've drilled holes very deep into the Antarctic ice and strung light sensors called digital optical modules, or DOMs, like a string of Christmas lights, deep in the ice, and the strings are cable that carry the signals to a central building with a bunch of computers in it. On those same strings, near where they emerge from the ice at the surface, we've placed a series of tanks about a meter across, and filled them with water, which then freezes. And there are two DOMs, two light sensors in each of these tanks.
These detectors on the surface form what is referred to as IceTop. It helps solve the mystery of cosmic rays that we cannot directly detect here on Earth's surface. That's why having detectors like IceTop and IceCube is crucial to scientists like Katherine. It provides a way to see the different effects of cosmic rays. But what are cosmic rays?
The particles that we're looking for are called cosmic rays. They are high-energy charged particles that are flying around the universe, flying around the galaxy, and occasionally hit the top of the Earth's atmosphere and produce sort of a shower of debris from the impact with the atmosphere. So the particles that IceTop is seeing is all of that debris. It contains things like electrons, photons, muons, various other hadrons. We are being rained down upon by these particles all the time, sitting in this room. The IceTop detector was built to study this shower of debris by collecting light for when those particles go through a tank full of ice.
A cosmic ray, at its simplest form, is a proton, which is the same as the nucleus of a hydrogen atom, which travels at extremely high speeds in space. But before knowing about how they interact at the top of the atmosphere, it's important to look at what kind of speed or energy they have.
In special relativity, when things get very close to the speed of light, 0.9999 and beyond, it starts to not be so useful to talk about their speed as the number of nines after the decimal point, as it is to talk about their energy. Because as you get closer and closer to the speed of light, the particles' energy increases. And so we find it more useful to talk about their energy than we do about their speed.
So these cosmic ray particles are very, very energetic. The detectors at the South Pole are tuned to specifically detect the particles that have a higher energy than the particles generated in our most powerful particle accelerators here on Earth, like the Large Hadron Collider in Switzerland. But wouldn't this mean that these particles are dangerous?
They would be if you lived in space, where they are. They are not dangerous to us here on Earth because we have a protective layer of atmosphere that shields us from these cosmic rays. They are considered a source of radiation. And if you're an astronaut living in orbit, you do have to monitor how much of a dosage of these particles you are absorbing by living up there unshielded by Earth's atmosphere. And if we were to make long space voyages out to other planets or other stars or wherever, we would need to put thought into how to protect ourselves and our equipment. The equipment aboard a spacecraft has to be shielded or hardened against this particular form of radiation.
So yes, they can be dangerous if we were to spend a lot of time in outer space. But here on Earth, we are safe thanks to our atmosphere. Specifically, thanks to all the air molecules. They act like a barrier between us and the cosmic rays. And since cosmic rays are highly interactive, it's similar to a bowling ball that goes really fast but loses its energy due to the bowling pins that it meets along the way. But if this is the case, wouldn't it be better to detect them in space? Or is it even possible?
It is possible to catch cosmic rays where they live, up in space. You have to send a detector up there, which means you can only build a detector so big. You can put a detector on a rocket or a balloon, or in orbit. There's one on the International Space Station called the Alpha Magnetic Spectrometer. So it is possible to detect them in space, but the higher the energy of these particles and the bigger of a splash they would make in your detector, the rarer they are to find. So to study the higher energy neutrinos, like IceTop and IceCube does, you need to build a detector that's too big to put in orbit or put in space. But here on Earth, you can make a very large detector by sprinkling sensors all over the surface of the Earth at ground level, like IceTop has done with its sprinkling of frozen tanks, a kilometer squared in size.
So even though space detections of cosmic rays are possible, having the option to build a very large detector here on the surface offers many advantages. It's like having a bigger net that allows us to catch more fish. But that also introduces a whole other challenge. Since the detectors on the ground cannot capture the original cosmic ray, then what do they detect? And what happens to the original primary cosmic ray?
So when the cosmic ray, the primary cosmic ray, which was what we call the original, the OG cosmic ray from space, when it has its first impact with some atom in the atmosphere, there's a cascade of particles creating other particles, creating other particles. The energy of each generation of these particles drops because it's being distributed amongst more bits of the particle shrapnel. And so the shower grows in size until eventually the energy of the particles becomes such that more of them tend to decay out than to produce more. And so the cascade then begins to subside. So the shape of the shower is increasing for a while in its development and then decreasing and kind of petering out.
So the primary particle that we are interested in dies as soon as it touches the top of the atmosphere. But since it's carrying a lot of energy, it will create a cascade, a shower of other particles that we can detect. How does this tell us about the original suspect, and how does it improve our understanding of cosmic rays?
The way IceTop works as a detector, what it's sensing is not really the particles themselves, but the flashes of light that they make through a process called Cherenkov radiation. When a charged particle goes through a medium like ice or water or air, it can emit light, not unlike the sonic boom emitted from a supersonic aircraft or the bow wake of a boat through the water. A particle going through a medium can emit a blue glow called Cherenkov light, and that's what the sensors are actually picking up. So where did the blue light come from is a question that the detector can't really answer directly. What we do is more like setting a bunch of buoys out in the ocean to look for boats. The buoys don't actually detect boats. What they detect are the waves given off as the boat travels somewhere nearby. So any one buoy bouncing up and down in the ocean doesn't tell you what kind of boat it came from or how far away it was or whether it was small or large. But what you can do is take all of the data from lots of buoys taken together and try to infer what sort of thing passed through the area. Was it a high energy particle? What was it? Was it a high energy shower with lots of particles in it that lights up a lot of sensors over a wide area? What's the timing of when the sensors were hit? You can use that to figure out what direction the shower came from, which is the direction that the cosmic ray came from on the sky. All those sorts of things are inferences about the primary cosmic ray that you're not detecting directly. You're just catching evidence of its splattering on the atmosphere. So it's actually a very difficult data analysis challenge to infer the properties of something you don't actually see directly.
The buoy example is my favorite at illustrating how the event is reconstructed. By taking data from all the different detectors and feeding it through the elaborate algorithms that physicists make, they can come up with a very educated guess on the cosmic ray's energy, type, and where it came from, among other things. These are very important to the puzzle. Knowing the cosmic ray's energy is a crucial clue. It is the astro part in astroparticle physics. If a cosmic ray possesses more energy than any particle created by any human experiment, it raises intriguing questions about its origin and the process that generated it. So what could produce such high-energy cosmic rays? And what does their origin reveal about the universe?
Because they carry with them such high energies, some cosmic rays arrive here with energies greater than we can achieve in the best particle accelerator technology humans have invented. There is something out in the universe powerful and energetic enough to make these particles. It's like saying, out there somewhere in the universe are natural particle accelerators that are more powerful than anything we have built here on Earth. What are they? Where are they? How do they work? And that cosmic rays are arriving at Earth with these energies is evidence that there are a class of high energy cosmic accelerators out there. And the fundamental question is, what are they? And how do they accelerate particles to these tremendous energies?
These high-energy cosmic accelerators and what they are is going to be the topic of the upcoming videos in this series. But can we know what the sources are? Meaning, wouldn't these cosmic rays point back to the object they came from? Well, the short answer is no.
Cosmic rays themselves are a hard way to study those objects because cosmic rays have electrical charge, so as they travel, they get bent by magnetic fields that they encounter along the way, like in our galaxy. The cosmic rays that arrive here have been wandering around the galaxy for millions of years, so they don't point back to their source. When you measure one, you can't just trace it backwards on the sky and say it must have come from there. That particular particle, its direction was randomized during its journey.
So since cosmic rays act like tiny magnets in a universe filled with large magnetic fields, their trajectory cannot be determined, and they do not tell us about where they came from. But the clue that they give us is about what sort of object they came from. So in some ways, they are tiny messengers from outer space that reach our detectors here on Earth, and with them, they bring some knowledge, a little piece of information that tells us more about what's happening in the vastness of the cosmos. This being said, cosmic rays are not the only particles that the IceCube Observatory detects. Some of these other particles actually do point back to their original source. These particles are called neutrinos, and they are the main reason why this observatory was built. So far, it has been very effective at catching them.
Well, the most exciting thing that the IceCube Observatory has detected is neutrinos of astrophysical origin. So IceCube is the largest neutrino detector in the world, and although there are plenty of things nearby that make neutrinos, like the sun or the Earth's atmosphere, IceCube was the first to discover a population of high-energy neutrinos that seem to be coming from an extragalactic source. So some very energetic object beyond our galaxy.
I think we are living in the most exciting time for scientific discoveries. By detecting particles like cosmic rays and neutrinos, we are figuring out this cosmic puzzle one piece at a time. And with every particle, there's a tiny message. I appreciate that you have watched this video until the end. I'd also appreciate your feedback. My goal with this video series is to share science and explain what kind of research is taking place now in physics and astronomy. I hope to do this by talking to experts like Katherine. Please tell me about what you think of this format and how you think it can improve by leaving a comment. And for now, clear skies.